Hi, everybody. Good morning and good afternoon, good evening, wherever you're located. Thank you so much for joining us today. My name is Jennifer McConnell, and I'm the product manager here at Protochips. And today is our third installment, our final episode of our webinar series called Closing the Pressure Gap, which is focused on doing high pressure gaseous experiments, looking at gas-solid phase interactions within the transmission electron microscope. We're highlighting how our Atmosphere AX system supports heterogeneous catalysis research at the nanoscale specifically, although it should be noted that that's not the only area of research the system supports, but it really is a big one. Because catalyst materials are typically in nanoparticle form, the TEM is really an ideal characterization tool with its powerful resolving capabilities, but the characterization of static materials before and after the reaction does not necessarily lend enough insight into the mechanisms that lead to, let's say, operational changes in the catalyst over time, where it degrades and starts losing activity, as an example. Over the years, technologies evolved in an attempt to introduce gases into the vacuum chamber of the TEM safely, to watch these materials undergo these mechanisms, and under more realistic environments with the hopes of getting that direct insight in how their structure is affecting their function over time. But the pressure of the experiment really is a major variable that can affect those results. And this webinar series is meant to give you a glimpse at what's possible today to create realistic, high pressure environments within the TEM using our machine vision software-based Axon AX system. Just in case you're not familiar with our company, at Protochips, we choose to focus on the entire workflow for in situ TEM. It's not just the TEM related hardware, because you can imagine everything from your sample preparation to the accuracy of your in situ parameters and the robustness of your in situ parameters, to how you collect your data and how accurately you're notating it, to how you manage that data and visualize it, can all affect your ability to properly scale your experiment from the bulk scale down to the nanoscale with relevance. That affects your reproducibility of your experiment, your productivity during the experiment, etc. So the short story being, your success lies in the entire scientific workflow. It's not just the hardware itself. And so Protochips is really looking at that workflow in its entirety and trying to support you in those areas. Okay, so we're really grateful to have you here. But before I introduce the star of today's webinar, I have a couple of housekeeping items to cover. Everyone's muted due to the audience size. We just want to prevent unintentional interruptions for our speaker while they're presenting. If you have questions, please put them in the questions box in the GoToWebinar panel, and we'll do a Q&A session at the end. And there'll be a short survey that pops up after the webinar, and we would greatly appreciate it if you fill it out. And there's a certificate of completion that will come in your email after the webinar if that's something that you're looking for. Okay, without further ado, let me introduce you to our speaker and tell you a little bit about her, and then I'm going to hand it over to her. So Dr. Sharmin is currently a postdoctoral researcher at the Synchrotron Soleil, focusing on the application of operando X-ray absorption spectroscopy, XAS, to study electrochemical systems. However, previously, she worked on operando gas phase electron microscopy applied to heterogeneous materials. With experience in both academia and industry, she's worked on various aspects of electron microscopy, spanning fundamental research, the study of dynamic behavior, examination of complex industrial materials, and the implementation of automated microscopy for high throughput sampling on an industrial scale. Dr. Sharna, thank you so much for joining us today. We really appreciate it and are looking forward to your talk. Whenever you're ready, I'm going to turn my camera and mic off, and the floor is all yours.
Thank you very much, Jennifer, for the kind introduction and for having me here. So, as Jennifer mentioned, my name is Sharmin, and today I'm going to talk to you about in situ STEM study to understand the morphology and evolution of copper-based material during high temperature redox reaction. So this study was carried out at the University of Strasbourg, IFP Energy Nouvelles, and Institute of Physics and Chemistry of Materials in Strasbourg in France. Right, so I will start by talking about the application of copper, because since I'm studying copper, and copper is a super versatile material, which has been studied using in situ TEM from the point of view of strain deformation, from electrocatalysis, from a corrosion as well as catalysis perspective. And as you can see, I have given a few examples here, how we can induce strain in the microscopy to study the fracture of copper. Here in the case of electrochemical CO2 reduction, how the material undergoes changes due to applied potential, or what happens to copper alumina alloy during corrosion process where you see phase segregation. Or in the case of catalysis, how the effect of different gas changes the surface morphology as well as the catalytic properties. So I will be talking about heterogeneous materials, but not from the point of view of catalysis, but from an application of chemical looping combustion. So the difference between CLC and catalysis is, in catalysis, we don't expect the material to go directly involved in the reaction, but in CLC, the material itself undergoes changes. But the material we use is heterogeneous and very similar to that of conventional industrial catalytic material. I will start give a brief overview of the chemical looping combustion process. Not everyone might be familiar with it. So we know combustion, which uses fuel to react with oxygen to produce energy, carbon dioxide, and water. Since we use air, the exit gas is diluted by the presence of nitrogen. As a result, the separation of CO2 is quite energy intensive. So in the CLC process, what we do is, instead of directly combusting with air, we use a metal oxide instead. Now, this metal oxide will give oxygen to the fuel for the combustion. As a result, what we have is pure form of carbon dioxide and water, which is easily separable. That's why we call it an inherent separation of carbon dioxide. However, during the process, the metal oxide itself will get reduced, and in order to regenerate it, we need to pass it down to an air reactor where it picks up oxygen and becomes oxidized. So ideally, we would like to have our material cycling again and again for eternity, but that's ideally the case. That's in reality, we usually have material degradation, and especially for this process where the material is undergoing a very high temperature reaction above 800 degrees Celsius. We have chemical stress induced during the oxidation and reduction. We also have mechanical stress, since in the industrial system, it's a fluidized bed reactor, meaning that the material has to constantly transfer from one reactor to another reactor. So what we want to understand in our study is the effect of temperature and number of cycles, and how all of these phenomena are related. So let's have a look at the material. As I said, it's very similar to that of conventional catalysis material. So we have alumina as a support for our active phase, which is a copper oxide. So the fresh material, as you can see, is mostly composed of homogeneously dispersed copper phase in the support. However, after about 300 cycles, we see that the material is segregating, and we see different copper oxide phases sintered and forming big chunks within our support. We also see that the structure of the support is also changing. From an initial mesoporous material, we form macroporosity, cracks, and fissures inside the material. So the objective here are to understand the material at two different scales. One is spatially, how the material is evolving. Another is temporarily, how the material is changing over time. So for the spatial overview, we have two different scales: how the material is migrating within the grains of the material, as well as particle growth and sintering of the copper phase. And at the atomic scale, or at the nanoscale, we want to see how the material is going in and out of the alumina to form reaction at such high temperature, as well as changes in the support behavior. So we will talk about that in greater details later on. And then in the time scale, we want to see how the phases and morphology evolve over the cycling and over time. So in order to do that, we have used a multi-technique approach. So using scanning transmission electron microscopy, X-ray microscopy, as well as in situ X-ray absorption spectroscopy and XRD. So today I will focus on two different techniques. One is the X-ray microscopy to understand the grain scale migration, and the other one is the scanning transmission electron microscopy. So the strategy that we have employed is to go from a simplistic system towards more complex system. So starting with unsupported copper oxide nanoparticles, just to see how the copper oxide or copper particle behave as a function of oxidation condition, like temperature, what is the phase, if it's a copper 1 or copper 2, and so on. And then we will increase the complexity towards industrial material. So going from copper oxide alumina nanoparticles to the grains and crush them and see under the microscope how they changes. So in order to do that, we want to understand the influence of the different parameters. So I will start by unsupported copper material. So we have initially studied this material, the unsupported or copper oxide nanoparticles in situ STEM. So in order to do that, we have used a GEM 2100F microscope at IPCMS, which is equipped with a Protochips Atmosphere system. Now, the previous speakers, they have already talked in greater details and beautifully about the evolution of the different atmosphere, different gas phase in situ TEM, like environmental TEM, the MEMS-based TEM, and the technological evolution given by the first speaker. So I will not go into that. Just to remind everybody so what we have here is our chip, where in between two chips we will sandwich our material. So in the top chip, what we call is where we have silicon nitride window, which is transparent to the electron beam, where we suspend our material, and then we have electrical contacts to give heating via Joule effect. So once we have that, we can introduce gas and temperature. So in our case, we have carried out a reaction at a temperature of above 900 degrees Celsius, and pressure of 1 atmosphere. That's the advantage of the MEMS-based system. And for the oxidation and reduction, we have used a 50-50 of oxygen and argon, and hydrogen and argon respectively. Now, so the model system that we have, how does it look like? So we have produced the copper nanoparticles in two different ways. So one is via producing thin film on the silicon nitride membrane, directly depositing via magnetron sputtering 1 nanometer thickness of copper layer, and then forming the nanoparticles under hydrogen inside the microscopes. So we kept a temperature between 280 degrees Celsius and 300 degrees Celsius. The protocol has been constant to produce a nanoparticle size of 1 to 10 nanometers. It's a bimodal size distribution, as you can see here, and larger nanoparticles of 20 to 50 nanometers. We have also synthesized some nanoparticles using thermal decomposition of copper acetate, where the nanoparticles were a bit larger, above 50 nanometers up to 100 nanometers. Now, once we have the nanoparticles, we wanted to see how the morphology of these nanoparticles changes once we have oxidation reaction going on. And we want to see how it evolves as a function of the temperature. If we increase the temperature, what is the size of the nanoparticles? And then in the next instant, we wanted to see what happens to the, what is the duration of oxidation if we keep the temperature constant. And finally, we did not have a look at the effect of gas pressure, but if we compare our study to that of literature, here we have a nice study by Lagro. It's a group from New York University. We have carried out a similar oxidation reduction reaction, but using an ETEM, and clearly we can see difference in the evolution of and the transformation mechanism as a function of the gas pressure. So this is an interesting comparison, and this really highlights the importance of pressure. Well, during the oxidation, so we initially have our nanoparticles, as I showed you, which is about let's say a size of 10 to 20 nanometers, formed under hydrogen at 300 degrees Celsius. Then we introduce oxygen, starting at a lower temperature of 100 degrees Celsius. So after about 1 hour of flow, we see a layer of oxide forming on the surface of the metallic nanoparticles. This layer of oxide from high resolution TEM we could identify as a copper 1 oxide, and also that matches with the information in the literature. If we increase the temperature to 200 degrees Celsius, we start to slowly form voids. And those voids eventually collapse to form hollow particles. Now, this can be termed as nanoscale Kirkendall effect. Kirkendall effect arises due to difference in the diffusion coefficient. Originally, this has been observed in alloy system. For example, if you have an interface of copper and zinc, if we apply heat, they will form alloy. But the thing is, one of the species, zinc, will travel faster than that of copper. As a result, the mixing will cause void when the zinc will displace. So this is a similar effect that we see in these particles here, due to difference between the diffusion coefficient of copper in copper oxide layer versus the diffusion coefficient of oxygen. We see that the copper will travel faster, as a result, leaving atomic vacancy, which will collapse to form void, and going towards the surface, leaving the core, leaving the hole inside the core. However, of course, the oxygen is also diffusing at the same time, so as a result, the particle will not grow twice in size, but we eventually form these nanovoids leading to holes. Now, if we increase the temperature even further, we see that these holes will eventually collapse, and this happens due to the minimization of surface energy, which will be more stable. The particles will be more stable once they're in compact form. So that's what we see in terms of the effect of temperature. Now, if we want to understand what's going on really in terms of the diffusion coefficient and if we can quantify it, we try to carry out the same oxidation, but now this time at a constant temperature, and to see how long it takes to form this hollow inside the nanoparticles. So as you can see here, we have carried out temperature versus duration to form the hollow nanoparticles, and for two different sizes. So one is 20 and another is 40 nanometers. And as expected, of course, the hollow particle will form will take longer to form at a lower temperature compared to that of higher temperature. So using a theoretical model proposed by Svoboda for such nanosystem and spherical system, we have calculated we have used an Arrhenius equation to plot diffusion coefficient versus temperature relation in order to find the diffusion coefficient at 0, as well as the activation energy to go towards this diffusion. What we see is compared to the bulk, and a similar study carried out using UV visible spectroscopy for lower, smaller nanoparticles of 10 to 12 nanometers, our study is in between, with an activation energy of 80 to 85 kilojoule per mole. And similarly, the self-diffusion coefficient is also somewhere in between the two. What we also see is clearly that the morphological evolution occurs as a function of temperature, oxidation duration, as well as the nanoparticle size, which are also important. Now we would like to see how the material changes when we produce a reducing gas. So when we introduce hydrogen in the system, this is what is happening. For the hollow particles, for example, here, we see the introduction of hydrogen leads to fragmentation of the nanoparticles into smaller particles from an initial copper oxide phase. What we try to understand is, of course, when we go from copper oxide to metallic copper, there's a unit cell reduction of about 0.6 times. Could it be related to this unit cell reduction? Or in larger particles of copper, there has been studies leading to the formation and of water vapor, which eventually creates pressure buildup and fracture of the nanoparticles. But those are usually seen in bigger particles. So what could be the possible reason? The possible reason, which we realized after carrying out multiple experiments using other types of gas like carbon monoxide or methane, is that this could be related to the presence of hydrogen. So what might be happening is hydrogen diffusing inside through the channels or through the defects inside the nanoparticles and forming reduction sites. And those reduction sites, those are multiple reduction sites, which eventually nucleates and grows. And once we have nanoparticles, they start to sinter and form these stable nanoparticles. So they undergo sintering until they're stabilized. So what we see is that the fragmentation, the reaction, it depends on temperature. Of course, the fragmentation is happening, but with higher temperature, the sintering effect will be more prominent. And it doesn't really depend on the shape of the original oxide, whether it's hollow particle or compact shape. We will see this fragmentation if the temperature is low enough to inhibit the eventual sintering. So this is quite interesting because this has also been observed for other systems, for example, for cobalt or for nickel, and often utilized as a form to regenerate catalyst when you eventually have bigger nanoparticles, which you don't want because it reduces your catalytic properties. Now, if we go towards higher temperature, what is happening is under oxygen, we see that at higher temperature, the material is forming faceted nanoparticles, even though they are more cubic-like structure. But under hydrogen, the shape is more spherical, faceted still. And we see that depending on the gas, it is indeed the case. If we come back to hydrogen, it will retain its spherical shape. Other observation involves how the nanoparticle growth mechanism is occurring. So for both oxygen and under hydrogen, we see three types of growth mechanism. One is migration and coalescence. So here, for example, here we see particles that are migrating to coalesce with the other particles, for example, in yellow. Or attractive migration and coalescence, whereby particles, they come closer, start to form neck, and then it eventually form a bigger particle. Or eventually oswald ripening, where one particle grows at the expense of another one. Usually a larger particle will grow at the expense of a smaller one, but it's difficult to identify because in this case, we did not see much of size effect or relation between size and the type of migration and coalescence or particle growth mechanism it followed. And finally, also at temperature of 700 degrees Celsius, if we keep the system at a constant temperature, we eventually see evaporation or loss of the both oxide and metallic form. So here I am showing you a video at what's happening to copper under hydrogen at 900 degrees Celsius. We see that the material starts to evaporate, and this evaporation is occurring unidirectionally. So we start from one point and then it reduces from in one direction. Under oxygen, or this is not really related to oxygen, but the size of the nanoparticles. If we have bigger nanoparticles, the nanoparticles will come out as smaller forms and those smaller nanoparticles will evaporate unidirectionally until all the particles are gone. So this was a very curious observation that we had, because in our real system, when we have our material, it doesn't undergo evaporation like this. So we try to understand what could be the possible reason. Now, this has been observed already for other metallic systems, like, for example, gold. Gold undergoes similar evaporation, whereas silver undergoes melting. But in this case, it's not evaporating from a liquid phase, it's directly evaporating from a solid towards a gas phase, so sublimation. So we try to understand what could be the possible reason behind it. Could it be that it's related to the support? Because since we have a silicon nitride on which we have the nanoparticles, which might not be representative of the alumina support because of the difference in the interfacial energy between the nanoparticle and the material. So in order to understand if the support might have an impact on this observation, this time we deposited alumina layer using evaporation of our silicon nitride, and then we formed the nanoparticles in a very similar way like before. What we see here is it's very strange. So in this case, for the alumina support, we start to see this evaporation effect at temperature as low as 600 degrees Celsius. So this is not what we expected. We expected that the metal would be, or the nanoparticles would be a bit more stable compared to that of silicon nitride, but which was not the case. So this was under hydrogen. And under oxygen, the behavior is even more strange because the nanoparticles, so we formed the nanoparticles of hydrogen. They were nice little nanoparticles of 20 to 30 nanometers. And then when we introduced oxygen as a function of the temperature as well as duration, we saw layer by layer growth. The copper phase would migrate and cause layer by layer growth like this without any specific shape. And then at higher temperature, this will eventually either sinter or eventually evaporate away. So we had to scrap the idea because this observation was very strange for us. And also after a couple of experiments, we realized that this might not be the temperature, this might not be the real temperature, because we have a layer of alumina on top of our silicon nitride. So this could be a false temperature, but so as a result, we were not sure what we were observing, and we have to scrap the idea. Now, to summarize what we have observed, we have carried out oxidation, and we saw, depending on the temperature, we can have Kirkendall effect, hollowing of the particles, shrinkage, and faceting. For the reduction, we can have fragmentation. And finally, at high temperature, we see particle faceting, different types of growth mechanism, and evaporation at above 700 degrees Celsius. So we try to understand what is causing the evaporation. In order to do that, now we would like to carry out our study using the industrial material, where we know that in the real system, we don't see such kind of evaporation. So what do we expect to see in the TEM? But before that, let's first have a look how the material is evolving. What do we expect from the material and how it's changing over time and as well as spatially. In order to do that, we have characterized it using scanning electron microscopy, XRD, and the one that I would like to highlight is STXM, X-ray microscopy, together with X-ray absorption near edge spectroscopy. So this technique is very similar to that of TEM coupled with EELS. EELS mapping would give us XY spatial information together with energy spectrum. So at each pixel, we have information about the oxidation state as well as the chemical speciation and where they're located within the sample. So we did that at copper LH and aluminum KH with a spatial resolution of about 42 nanometers in order to identify where the copper is located, what is the correlation between the copper and alumina. So the sample was prepared by ultramicroscopic cut of 100 nanometers in order to preserve the grain shape, as well as for the sample to be thick enough for the X-ray to pass without self-absorption. So here we are with the fresh material, which is composed of copper aluminate. So copper at when we impregnated and calcined the sample to have this sample, it reacted with the alumina to form copper aluminate. And we can see that the copper concentration is more or less homogeneous inside the grain, but it changes towards the edge, which is a bit rich in copper. And in some areas, we see changes in the support structure. The initial support is alumina, gamma alumina, but here we also see some alpha alumina form. Sorry. So now, if we cycle the material, so once we reduce the material, the copper will come out in terms of metallic form. But then again, once we cycle back under oxidation, it will go back and react with alumina to form aluminate. So we do that for 50 times, and we see that the material now, after 50 cycles, is composed of several different morphologies. We can identify 3 different areas. Area 1 here, for example, if we zoom in at this point, we see area 1 is composed of compact shape, mixture of copper and alumina. Copper aluminate still from signature of LH, but the amount of copper is lower, which we get from the EDS. And then here we have area number 2, which is at the interface between this porous region and this compact region. This area number 2 is copper aluminate as well, but this time it's richer in copper. And then we have the area number 3, which is composed of large porosity, macroporosity, and it's mainly composed of alpha alumina. That's something that we get from the signature of aluminum KH. And within this alumina, we see copper in form of oxide. And here it's copper 2 oxide and not copper aluminate. What is interesting as well is that here already we can see the direction of migration. So when we, direction of migration of copper, when we reduce, the copper comes out, goes towards the alpha alumina, and then during oxidation, it comes back towards the remaining of the alumina to react to form copper aluminate. Now, after about 200 cycles, what we see that the material is now completely transformed towards alpha alumina, and there is no more copper aluminate left. Instead, we have copper oxide. So clearly we see in this case, the copper oxide is segregated within the alumina network. And after more cycling, we see that the copper oxide will eventually form very big particles. So what happens as a function of the cycle is that with cycling, copper aluminate decreases and we have increase of the copper oxide. We see transformation of the alumina support and eventually only copper oxide and alumina remains. And with further cycling, the copper oxide phase undergoes sintering. So this is what we know so far about our sample from other characterization techniques. Now, what more can we understand? Using in situ STEM, we wanted to visualize how this movement of copper going in and out of the alumina, and if we can eventually quantify this diffusion mechanism and reaction. Eventually, how the phase transition of the alumina support is occurring from an initial gamma alumina or copper aluminate, how is it transforming to a more compacted alpha alumina form and changing all this porous network. So with this objective in mind, we have put the sample, we crushed the sample, and we put in the microscope. So at low temperature, when we carry out oxidation and reduction, we see at 300 degrees Celsius, similar observation as we have for our model nanoparticles. So we have copper oxide that is undergoing fragmentation under hydrogen, and then formation of hollow particles at this temperature of copper oxide. Now, if we increase the temperature, let's see, we have copper oxide and copper aluminate mixture, and we have introduced hydrogen. At 400 degrees Celsius, the copper aluminate will be reduced to form these metallic nanoparticles that you can see here on the surface, and it also agrees with the XRD data. However, when we reintroduce oxygen at 700 degrees Celsius, we see that the copper oxide migrates away from the alumina support. So in this case, so all the copper oxide that was here before, they're gone and accumulated in other areas. So for example, here you have accumulation, big particle of copper oxide, and here on the silicon nitride membrane, it's full of copper oxide. So it seems like copper oxide somehow prefers silicon nitride compared to alumina. And then when we heat it to 800 degrees Celsius, we don't see copper anymore. After 30 minutes, we see the copper. When we played with this with the focus of the microscope, we see some copper got deposited on the non-heated chip, so on the other chip. So clearly we see a temperature-dependent migration of the copper within the support, as well as migration, evaporation, and redeposition maybe on the other chip, which is not heated. But good news is we saw some local changes in the morphology and structure of the now copperless alumina. And if we do selected area electron diffraction, we could see some planes related to the alpha alumina. So we were partially happy. Then we realized that could it be related to the material itself, that the effect that we crushed our material and then we suspended in that could link to this migration effect. So can we confine the copper oxide into a nanoparticle form? So in order to do that, we have specifically synthesized nanoparticles of copper oxide and alumina. And as we can see here, this material is composed of copper aluminate. And even under oxygen, when we increase the temperature, the copper oxide seems to come out, which should be stable. The copper aluminate phase should be stable, but even at such temperature, the copper oxide is coming out. We have carried out multiple experiments by varying the gas, for example, introducing oxygen, hydrogen, and but the evaporation at higher temperature persisted. But again, good news is we could see the alumina phase transition. Now, if we compare it with our system, let's say, which we don't see, and now, but the thing is, in the TEM, we realized that it might be related to the cell. So we took the cell, deposited our material, and ran the reaction inside a furnace. So this time we took the silicon nitride chip inside the furnace, and we carried out 2 oxidation and reduction cycles at 900 degrees Celsius. What we do see is even after 2 redox cycles, we still have copper. So that's happening in the furnace, but in the in situ stem, no matter what gas we use, what temperature we use, we eventually have evaporation at high temperature. And when we do the postmortem analysis using a scanning electron microscopy, we see that the copper got deposited on the non-heated chip, and some got deposited on the area directly above the heating area, and others got deposited away from where the heating area was initially on the heated chip. So we see clearly 2 differences. One is the effect of the experimental parameter, so the reaction condition. So high temperature is not really suitable for this material, and also the experimental setup that could eventually lead to this discrepancy. Eventually, we carried out other tests, and in one of the tests, we saw that under hydrogen at 900 degrees Celsius, we could eventually stabilize the copper for more than 1 hour. That led us to think that could it be eventually related to the thermal conductivity of the gas? That if we have a higher conductivity gas like hydrogen compared to that of oxygen and argon mixture, we might have better heat distribution within our three-dimensional volume, and as a result, it's quite homogeneous, and you don't have temperature difference, which might lead to this evaporation or this migration. So we decided to carry out experiment using a mixture of helium and oxygen instead of argon. So in this case, we have carried out from 25 degrees Celsius to 900 degrees Celsius and back to 25 degrees Celsius about 2 times. So in the first cycle, so this is the initial material, which is composed of homogeneously distributed copper inside alumina. And then after cycle 1, coming back and to do EDS, we see that there are still copper remaining, except in some areas which is depleted, where the copper is gone or less. But in the second cycle, all the copper is gone. So we could eventually make copper stay for 1 cycle under such temperature and gas mixture. And what we realized is, depending on whether the window is located towards the gas or away from the gas, we see some differences. In one case, the evaporation was faster than the other. So with this in mind, in order to summarize what we saw for our nanoparticle system, we could visualize our material at different temperature and at gas at different atmospheric pressure, which is closer to a real reaction condition. And this real-time visualization allowed us to have a quantitative understanding of the morphological evolution. But unfortunately, the reactor configuration is important for some system, and clearly for copper it was quite important, because I have also carried out studies using other metal, and it's only very specific to copper. So unfortunately, the failure in our experiment is attributed to a combination of factors, including the material itself. So in this case, copper, the setup of the reactor, which is only allowing us to heat just on the chip and not the whole volume, which might not be representative of a real system, of a real reactor or a furnace, as well as the composition of the carrier gas. So whether or not the gas has high thermal conductivity, for example, might lead to difference in observation. So bearing all this in mind, we should be careful about the different parameters, and be careful to compare with other techniques and other setups, and really focus on the difference between the different setups. And so this is where I summarize, and I would like to acknowledge all the people that contributed to this study. So this was part of my PhD, which was carried out at Energy Nouvelles in collaboration with IPCMS and Soleil Synchrotron. I would like to thank everybody that helped me during 3 years of this work. And with that, I would like to thank you for your attention. If you have any questions, please feel free.
Dr. Sharna, thank you so much for that talk. That was really, really interesting. And the combination of all the different techniques that you used was really nice to see how it helps with the totality of the story, the totality of the circumstances. If anybody has any questions for Dr. Sharna, now's a good time to go ahead and put them in the questions box if you haven't already. We do have a handful to start with, and we've got a good amount of time for questions. So let's see here. So first question is, were there any special tools you used when sputtering the copper onto the chip to help kind of contain your sample? You'd mentioned, I guess, sputtering at the beginning. How did you sputter onto the chip?
Okay, right. So the challenge was to not sputter copper on top of the gold contact, so not to change the resistance and the heating system. So in order to do that, we have to protect the contact. We did that by covering with Kapton tape.
Gotcha. Okay. Yeah, there's a lot. We know a lot of people. I think we used to recommend that too sometimes. There's also back in the day, we used to tell people to punch out their windows to kind of create a mask out of some of the chips for the chips that you're not using as well. But good on you. Okay, great. Did you notice if any specific facets of the copper nanoparticles were more active than others, or how the facets may have changed the activity or your observations?
I mean, no, we haven't really looked into the faceting aspects or regarding the surface, because since we are not really involved with catalysis, it did not really affect us.
Okay, great. The next question is, did you notice any beam effects, or would you expect any of these processes to be beam sensitive?
No, typically the material we have used, it was in STEM mode, so the beam was already quite low, and for the observation, we did not do continuous exposure to beam. So I wouldn't expect this phenomena to be related to the beam effect of the beam.
Okay, great. This one was pretty straightforward. Were all your experiments performed at 1 atmosphere of pressure?
Yes.
Okay, that was an easy one. What would be the ex situ tests that you would recommend performing before going into the TEM? I guess I interpret this as, is there a set of ex situ tests to characterize a particular sample set that you would recommend so that you have a full understanding of your sample before you go into the TEM and doing in situ?
Yes, yes, that would be. I mean, of course, I would not be able to recommend for model system like that we did for the nanoparticles. That is super specific to the TEM. I wouldn't know how you can do without the presence of TEM. It has to be in glove box, and it has to be because it's sensitive to air if you want to do oxidation reduction. But for the samples for the actual material, the industrial material, supported material, you can do a range of tests. Like for our case, we did SEM, we did XRD, we even did in situ XRD to be sure to know what we expect. And a combination of techniques have allowed us to already have a very good understanding of the material, and then to understand the nanoscale evolution, go for the TEM.
That's great. And that was a great question, because I think what we see a lot is you get a lot of people really excited to go and do some of their in situ TEM tests, and they may not have done a complete set of ex situ results yet to fully understand what they think they're going to see in the TEM, and then they start going down some rabbit holes, that may have been answered with some ex situ experimentation beforehand.
Yeah, no, that's one of the things. If we hadn't done a lot of ex situ characterization before, would have taken the TEM observation for granted, saying that okay, it's this material, it evaporates, and it's related to the material itself. But since we have already have a lot of experience with our material, with other techniques, with that gives us information about the morphology, about the oxidation state, both in situ and ex situ, we were already quite aware and knew what to expect.
Yeah,
you can plan it better.
Yeah, exactly. It's so important. It's so important. The more that we can help the community understand that aspect, I think the better for everybody. So that's great. Thank you so much. There's a couple more questions here. Let's see. Do you feel like the amount of oxygen in your reaction could tune your Kirkendall effect, and maybe therefore the final copper nanoparticle size?
Yes, I think so. The amount of oxygen, if we, for example, I would definitely think if we change the amount of oxygen, let's say going from 50% to 100% oxygen, it would definitely change the kinetics of the reaction. However, and which is also, that's something that I mentioned, that if you do your experiment at lower pressure, the observation would be very different. So yes, definitely, I would expect the kinetics to be changed, and as well as in some instances, if the pressure is too high or too low, the mechanism would be different.
Yes, that makes a lot of sense. Good, good. And then we have one final question. If anybody else has any questions, go ahead and enter it in your chat box now. Have you ever considered analyzing the gas output with your reactions? It sounds like the activity wasn't too important in this particular case, but would there be any benefit to like mass spectrometry with an experiment like this?
In our case, we didn't really have to, for this particular case, we didn't really analyze the residual gas, because we're not really concerned about the activity. We are expected to consume everything, and we don't really care, because in our case it's not specific product that we're looking for. But in other cases, definitely, when we carry out catalysis, for example, Fischer-Tropsch or other catalytic reaction, that time we are concerned about the product. As a result, we would like to know what product we are getting, and we can eventually correlate it with the catalytic activity. People have done it already, and we in our group, in our X group, we have done it already.
Yeah. That's oh, I got a clarification on the question. I may have morphed it incorrectly. They clarified to maybe just, would you use mass spectrometry to maybe see the water content at the start, as the water content may have an effect on what you're doing?
Yes, we did have a look, but the content of water, it would be more related to for example, if we are doing reduction, it would be related to the amount of reduction. But no, I don't know how it can influence things or the observation that we had.
Okay. I think we've made it through all the questions now, but it's not unusual for a question to come in after the webinar when people watch it, rewatch it later. So if there are questions that come in, we'll certainly share them with you, Dr. Sharna. Again, thank you so much for joining us today. It was a really great talk and really important points on having multiple different types of techniques to surround your in situ TEM results to really understand a full story. So thank you again. We look forward to seeing you in a few weeks in Strasbourg. And yeah, I hope you have a great day. Thank you everyone for joining us.
Thank you very much.
All right, bye, thank you.